Hello everyone, welcome to our session for today. So we are going to discuss the kinematics of particles today. And since this topic is a very long topic, so we'll just limit our discussion to these two parts, from the outline. Okay, we will divide still these parts here into perhaps 2 to 3 videos because this is already a very long topics. All right. So for our introduction, this is just a very brief of our introduction because we have done this twice already. So we have here the kinematics, is the geometry of motion. Okay, kinematics is geometry of motion. So motion of the particle. So the motion of the particle can be constrained or unconstrained. Then we have here choice of coordinates. You can use the rectangular coordinates, x, y, z, cylindrical. We have r, theta, z. So like this one. So r, theta, and z. Okay, same to this one. And for spherical, we have capital R, theta, phi. So capital R, theta. So this theta here. And we have phi, this one. Then we have here the path. Path, if you look at this coordinate system, and then this coordinate system, we have the plane. So we have here the path nt, nt. And then we have reference frame. So I'll be talking about absolute motion and relative motion for this part. And we have a very nice materials class to discuss this part in our future lecture. All right. So now we have here the rectilinear motion. Once again, we have here the 4 items that I need to do for this part. So we have to describe it. So what is this? The basic concept about rectilinear motion, the sign convention with reference to this illustration here, the position, displacement, delta S, position S. All right. So we have here the broken line as our rectilinear path, the path where the particle will be moving. So we have here a point O, this is our fixed point, fixed reference point, and we have here point P where the particle stop moving, and point P prime where the particle moves farther from point P. And then we have here what we call the displacement. But before that one, so for the sign convention, so if the particle is moving towards the right from this reference point O, so we have the positive displacement class. Okay, so if it moves to the left of this uh, fixed origin or the point of origin, so this is negative. Okay, so we have here the S is the position from the original position of the particle at point O. This is the reference point. The particles moving to the right at this point P, covering this distance. So of course it takes time for the particle to move up to this point. So we have here the time t. And if the particle moves farther from this point towards P prime, so we have what we call displacement, and we represent this by delta S. So delta S. And similarly, for the time, if the particle moves towards P prime from P, then we also have what we call the time increment. No? We call it delta T. Okay, so delta T. Now for the velocity, so we have what we call average velocity, denoted by this or by the symbol V subscript a v. which is equal to delta S divided by delta T. Can you still remember what is the unit of velocity? So if you can still remember, we have this unit meter per second. Okay, so that refers to velocity, or we have feet per second. So again, this refers to velocity. And we have kilometer per hour, km per hour. So that's also velocity. Or we have miles per hour. Okay, so this is velocity. So if you look at the unit class, so the unit above meter, so that is for the distance. S is for the time, so distance time. So when you speak of velocity, so the unit is in terms of distance per unit time. Okay, so that is our velocity. So to easily remember, class, so this is the basic concept about velocity. Okay, so similarly, so as mentioned in the previous slide, so we have here the time for the particle to move from point O to point P. And then there's an increment of the time when the particle moves further to P prime. Alright, now when we speak of average velocity, this is just the ratio. The ratio of this delta S and delta T. So this is our average velocity. Alright, this is our average velocity. Oh, sorry, this is V. So average velocity. Then we also have what we call instantaneous velocity, and that is represented by this symbol V, which is equal to ds over dt. Or we have this S dot. It means that we are differentiating the position with respect to time once. All right. Now for the convention, if the particle is moving forward to the right, and where V is greater than 0, okay, so it moves to the right of this position, fixed position. Or it could be that V particle is moving to the left, so V is less than 0. Okay, now for the speed is just related to the velocity. Speed is just the absolute value of the magnitude of the velocity. So if you're because velocity can sometimes be a negative, so if the result of your calculation for the velocity, the magnitude of it is negative, so you just take the absolute value, and that would be the speed. Of course, the absolute value of positive number is also positive. All right, and when we speak of instantaneous velocity, that is the velocity at any instant given time. So for example, you're asked to find the velocity at this point. Okay, so we have here the instantaneous velocity v at this point, which is defined as ds, or the derivative of the displacement with respect to time. Okay, then we have what we call acceleration. So acceleration is defined as the ratio of the delta v and delta t. So it means this is the, when we speak of velocity class, that is the rate of change of the displacement with respect to time. Okay, so if you have the particle moving towards this direction with a velocity of v, okay, up to this point here, and then of course there's a corresponding time, no? Corresponding time to reach that point P. And assuming that the particle moves farther from point P to point uh, P prime, so we have a t here, so we have here the increment of time. We can call it, we can call this as delta t. Of course, if perhaps there would be a change, no? Change of the velocity, you know, from this point to that point, so you can call that, we can call it as delta v. Okay, delta v. So to find the average acceleration, you just divide the delta v by delta t. So you have now the average acceleration. Now for instantaneous acceleration a, so that is defined as the derivative of v with respect to t. Or in symbol, we have the v, then we have here the dot above the v. Or this is equivalent to s double dot. So it means that you are differentiating the position twice, and you got the acceleration. Okay, and note the symbol class. Acceleration could be equal to this v dot, and or this is equal to s double dot. So that's our acceleration. For the sign convention, we may find that the acceleration could be positive, no? If the particle is moving towards the right and with the increasing velocity, all right. Or still, if it's moves to the right, so acceleration here is positive, no? If the, so acceleration is positive, meaning greater than zero, if the particle is moving towards the right with increasing velocity. Okay, towards the right, so going to the right with so towards the right with velocity increasing. So the arrow above means the velocity is increasing. But the acceleration is negative if that is still positive if still going to the, so this time going to the left, so going to the left, but velocity is decreasing. Or to make this clear class, I will show you the sign convention here in the other materials. This is well explained in the other material. So it depends, even if the particle is moving towards the right, so it can be that the acceleration is negative. So it depends on the situation. Like for example, if the velocity is decreasing, okay, so it is shown here. All right, so here's the better explanation of the sign convention class. Okay, so consider particle with velocity v at time t. Okay, so we have here the illustration which is similar to the one that I have shown a while ago. So we have here a particle moving from this point to other point. So in our previous illustration class, we assumed that the particle moves from this point O, okay, and it takes time t to reach at this point P. Then we have here the velocity, velocity of the particle moving towards this direction to P prime. Okay, so perhaps at this point the velocity is v, and then as the particle moves further, it could be that the velocity of the movement of the particle is increasing with this increase of delta v. Okay, so in our calculation for the instantaneous acceleration, a is just the limit of the delta v with respect to t as delta t approaches to 0. Now for the sign convention, so we have here the acceleration greater than 0, meaning it's positive if, so the instantaneous acceleration may be positive if increasing positively or positive velocity. It means that if at this point you have the velocity as the particle moves from this point towards the right, and we have this velocity, and then we at at this point here, sorry, at this point the velocity increases this much delta v. So we can see that the velocity changes from v to v plus delta v. So in this case, so the instantaneous acceleration is positive because there's an increasing positive velocity. So increasing in the sense that it goes towards the right, and increasing in a sense that the original velocity added with some increment of the velocity. In this case, we have delta v. So positive plus positive velocity. Or it can be decreasing negative velocity. Decreasing negative velocity. So when will that happen? So in this case, class. So still positive. Okay, still positive. But you see it pointed or directed towards the left. But you see we have initially this much. Okay, so if you look at the arrow, we'll just look at the arrow. No, the greater is the arrow, then the faster is the particle is moving. So you see here, this much of the arrow for the v. So this indicates higher velocity. Then if you look at this, lower velocity. So there is a decreasing, decreasing negative velocity. Okay, so decreasing negative velocity. Now here we have v, so this much. Then we have v plus delta v. So mahaba tong arrow na to. So increasing. Okay, so increasing. So instantaneous acceleration may be positive if increasing positive velocity or decreasing negative velocity. So these are the scenario class when the acceleration becomes positive. Okay, so positive in these two scenarios, that the velocity is increasing. Okay, so increasing. So galing sa maliit, lumaki from smaller arrow to bigger arrow. Then on the other hand, we have here the illustration from bigger to smaller. Okay, so decreasing negative velocity. So still our acceleration is negative. Sorry, positive for this scenario. The other scenario is this one. This will be negative. Okay, so there are two possibilities also when the acceleration becomes negative. So this becomes negative class if the particle is moving towards the right and the velocity is decreasing. So you see here, longer arrow than shorter arrow. So it means that it's decreasing. So decreasing positive velocity, positive in the sense that it is directed towards the right, but the acceleration is negative. Okay, and another possible scenario is that here, so it pointed or it is directed to the left, but you see the velocity is increasing. Originally this is a shorter arrow, and then this is longer arrow. So it increasing, but it is directed towards the left. So in this case, the acceleration is also negative. All right. So remember these two concepts, class. This is very important when we speak of instantaneous acceleration. All right. So we'll go back to the original slide. All right. So that is for the sign convention. Then other differential relationship. So we have here A equal to V uh, dV over ds, or derivative v with respect to the position. And this is given also as S double dot. No, S double dot equal to S single dot times the derivative of S single dot with respect to position. Okay, so where this formula is taken from, class. Okay, so originally this is taken from, you know that we have this relationship that V is equal to derivative of the position with respect to time, right? So from here we can solve for dt. So dt is equal to, we have ds divided by v. Okay, so we can call this equation as our equation 1. So let's call this equation as our equation 1. So this is our equation 1. And we also have a. So we know that a is just the derivative of v. So a is the derivative of v with respect to time. Now if we are going to consider this as our equation number 2, and if we are going to substitute 1 in 2, so substitute 1 in 2, so what will happen? So our acceleration becomes a equal to, we have dv divided by, so what is our dt? Dt is equal to ds over v. So we have now division of fractions. So what is the rule of in dividing fraction? So the rule is to invert the divisor. So this is our divisor, class. Invert the divisor and proceed to multiplication. So this will be dv. In times you invert this one, so we have v ds. Okay, or rearranging, so we have a equal to v times derivative of v with respect to s. Okay, so this is what you have seen in this equation here. Okay, so that is where this formula is taken. All right, how about this? So this one is just we know that v, no? So we have v is just equivalent to s prime. Sorry, not s prime, but s dot. Okay, so that is the equivalent, and we also have dv. So dv is equal to, so meaning you take the derivative on both sides or differential on both sides. So we have something like this. All right, so substituting, we have our s, our a here is the equivalent to s double dot, right? So substituting here, so we have s double dot equal to, our v is equal to s dot, so we change this to s dot, and we have dv is equal to ds, so ds over, so we still have ds here. All right, so these are the equation for the acceleration. Okay, so I hope you understand that concept, class, and I will not make this video a very long one. We'll continue the next slide on our next video. So thank you very much, and hope to see you in our continuation of this our lecture. So for now, bye. See you again later.